Good afternoon, everybody. So that video was a little preview of what we're going to be talking about today. Have just a couple of announcements. Again, midterm number 1 on Monday, October 25th from 4 to 5 p.m. You will be able to find it on iLearn on that same place where you can find a demo test right now. So that demo test will be available until Sunday. I saw that a few of you have taken it, but if you want to make sure that you know how to access a test, please try it before Sunday night so that on Monday you'll be ready. Again, I will be logged on to Zoom, this Zoom session, the lecture. So if during the test you have any questions, that's the best way to find me. Just join the Zoom session and ask me questions through chat. You can email me too, but it might take, sometimes there's a delay in the email and it might take a little while for me to get it. So I think Zoom is best if you can. You do not have to come to Zoom on Monday. It's completely optional. It's just if you have questions about the test, you can come and ask me through the chat so that you don't disturb other people. Will demo test answers be available to us? No, I didn't set it up that way. We can review them if you want later, maybe at the end of this class. If you have questions about it, I'll be happy to. And the total number of questions is about 30. It might be 31, 30, 32, or 29. I haven't finished writing the test, so I don't know yet, but it will be not just multiple choice. There's the ordering questions and true and false. So very good. I got a lot of questions about this on Wednesday's lecture. People were asking me if there will be a homework number 4, and the answer is yes. I will be posting it after class, and yes, you will have a quiz next week. So I know that it is a little hard because you have to study for the test and then you have to do the homework. So just it'll be, you just have to work a little more this week. But hopefully, since you have the chance to go to discussion section and get all your answers, all your questions answered, hopefully it'll be fine. It's never been a problem in the past. All right. So today we're going to finish talking about star formation, and we will just barely start talking about exoplanets. So these chapters from the textbook are from both today and for Wednesday. And again, none of this will be on the test. The test only covers lectures 1 through 9. So very good. All right, so this is the last thing that we talked about last time, thermal radiation or thermal light. And it's the idea that everything in the universe, pretty much everything that is made of normal matter, emits light. I emit light, you emit light, the earth, the chair where you're sitting, stars and planets and asteroids, everything emits light. It's just that sometimes it is light that we cannot see with our eyes. The kind of light that an object emits depends on its temperature. So hotter objects will emit light that is more energetic, and cooler objects will emit light that is less energetic. So this is what is called black body radiation. This is the physics term for it. And radiation just meaning light. So a hot object, this is a graph of how much light. So on the y-axis, it shows you the amount of light that it emits at any given wavelength, which is on the x-axis. And I'm not asking you to remember units or specific numbers, but you should remember that the visible light that we can see is only a small part of the electromagnetic spectrum. And then we have at longer wavelengths, longer than the light that we can see, we have the infrared, which we will be talking about today a lot. So infrared light has longer wavelengths than visible light. And then on the other side, right, on the short wavelength side, we have ultraviolet light. So you can see how, for example, a star that has a surface temperature of 15,000 Kelvin will emit a lot of light in the ultraviolet and not so much light in the far infrared, right? But the part that we can see is very small, right? The only part that we can see of the electromagnetic spectrum is the part that is colored in the rainbow color here. So a star that is 15,000 Kelvin, we will see only as far as the, the ultraviolet or the blue light, and so on. So the amount of light that an object emits also depends on its temperature. So the hotter an object, the more light that it emits per unit area. So that means if you have two objects that are exactly the same size, exactly made the same thing, but one is hotter than the other, the one that is hotter will be emitting a lot more light, and the light that it emits will also have more energy. So it will be more energy. If you remember, more energy means shorter wavelength, and it means higher frequency. So the other object, the cooler object, will emit less light, and the light that it emits will have a longer wavelength, less energy, and lower frequency. All right, so let me ask you, if you look at stars which are emitting light just based on their surface temperatures, so if you look at stars, which one is hotter? A blue star, a red star, or a planet that only emits infrared light? So which one is hotter? A blue star is A, B is a red star, and C is a planet that emits only infrared light. Right, so which one is hotter? A blue star, B, a red star, C, a planet that emits only infrared light. Right, so let's see. All right, that's correct. The answer is A blue star. Let me see. Let me try to explain this in a little more, in a different way. So let me share a different screen. This one. So you can find this on a website, which I included in the slides. So it is just an applet that allows you to see this curve, this black body curve, as a function of temperature. So you can make it hotter or you can make it cooler. And you can see how, so again, on the y-axis, right, on the vertical axis, what you're seeing is the amount of light. So if it's higher up, right, if it's up here, it means more light. So a hotter object will emit more light. So we actually have to zoom out. So a hotter object, the hotter it is, I'm going to higher and higher and higher temperatures, and the more and more and more light that it emits. But also notice how the peak, so this peak, that's where it emits the most light. Notice how it shifts. When you go to cooler temperatures, that the peak is, for example, here, like in the yellow, in the green, you go to cooler temperatures even. I'm going to zoom in again. And you go to cooler and cooler and cooler temperatures, like such as the temperature of a planet. Let's go I need to zoom in even more. Notice, oops, okay. So notice how the peak now is way in the near infrared. So this is visible. Here is this is infrared, and on the other side over here is ultraviolet. So the Earth actually emits only infrared light. So you can't see a planet. You cannot see the light that a planet emits with your eyes, because your eyes are not sensitive to infrared light. Your eyes are only sensitive to this region here with, all the colors. You would need to, so a planet, you see it because it reflects light. So you can see the reflected light, but you can't see the light that it emits unless you had a special camera that was sensitive to infrared. So let me go, no, the other way around. Let me zoom out and let me go back to the temperatures. A light bulb, for example, it emits mostly infrared light, but it emits some light that you can actually see. So a light bulb, you can see it with your eyes, the light that it emits. So because there's some red light, there's some green light, there's some blue light, so you can actually see it. Let me zoom out a little more and get back to the range of stars, where you have thousands of degrees Kelvin. And so you can see how blue star is hotter. Why is it blue? Because most of the light that you can see is blue, whereas a red star has a lower temperature. And again, I have to zoom in again. And then for a cooler star, most of the light that you see is actually red. So, okay, so a question, is that why snakes can see infrared? Because they are sensitive to it. Yeah, so their eyes must be different. They must have different sensors, different from our cones and rods. And so and not just snakes, there's many animals that can actually see infrared light. And we're going to watch a video a little bit related to that. Based on the thermostat, does that mean that a light bulb is hotter than Earth? Yeah. So Earth is fairly cool, right? Like it's like room temperature. Whereas a light bulb gets pretty hot. Like if you touch the Earth, touch the ground, it's not going to burn your hand. If you touch a light bulb, it probably will burn your hand. So that's right. Let me go back to sharing my slides. And all right, so I sort of answered this already. Why does the sun look yellow? Well, the sun has a temperature of about 5,000, 6,000 degrees Kelvin. And the curve that corresponds to that temperature has a peak right around green, yellow. So it turns out that just the way that your eyes perceive the colors, the yellow kind of wins over the green, and that's why it looks yellow. But it is just, why does it look yellow? Because the surface temperature is such that most of the light that it emits is yellow. So this is a question that is going to be on your homework, actually, the one that I'm going to post tonight. So does a blue star emit light of any colors other than blue? So this is an example of a star that is 8,000 Kelvin in the surface, the photosphere, and you see that it looks blue. Does it emit light in any other colors? Yes, of course it does. It emits red light and orange and yellow and green and everything. It's just that what your eye picks up is the one that it emits the most, and it emits mostly blue light, right? I mean, our eyes are not very good at picking the indigo, which I guess is the next one, but it looks blue for the most part. Whereas a cool star, a much cooler star, it also emits some blue and some green and some yellow, but the most is red, and that's what your eye picks up. All right, so.
Professor, I have a question.
Yeah.
So according to this law, so that we cannot see the core of sun because the temperature is so high, so its peak will be the ultra light, and we cannot see it.
Okay, so good question. So first of all, we cannot see the core of the sun because it is very deep inside the sun, and everything else that is above the core blocks our view from the core. So we're not able to see it. However, if we were able to see the sun, the core of the sun, it would look blue. Do you understand why it would look blue? I mean, you're right, it would peak at, it would actually, in the entire electromagnetic spectrum, it would emit most of its light in X-rays, which we cannot see X-rays. So you're right about that, but we still would be able to see it, and it would look blue. And the reason it would look blue, let me go back actually to the, where is it? Would go back to this. The reason it would look blue, I mean, you would have to go way up, and the peak would be way, way, way on the left, right? There would be very, very high energy. It would be X-rays. The reason it would look blue is that in the range of colors that we can actually see, most of the light would be coming from the blue. So yes, you're right that, I mean, we would not be able to see the peak. We would not be able to see most of it, except if we had an X-ray telescope. But to our eyes, it would look blue.
Okay, thank you. Got it. Yeah.
Great.
Wouldn't the core of that star be like purple?
Yeah. I mean, the bluest possible, right? So thank you for clarifying that, because from now on, for the rest of the quarter, every time that you hear me say blue, what I mean is the bluest, or sorry, the shortest wavelength possible that we can see, which is technically it's purple. It's just that, as you know, astronomers, we usually just say blue versus red. So the limit on the left, we call it blue, and the limit on the right, we call it red. But yeah, technically, it's not really called purple. It's what is it? Violet. Violet is the technical term. Right. Very good. So let me go back to the slides here. Great. So I'm actually going to show you a video right now about infrared light. And I do apologize because it is a video for K through 12. So it's a little silly, but I like that it shows some really nice illustrations about infrared light. So let me show that right now.
These days we're all familiar with night vision cameras, but how do these things work? How is it that you can just turn on this camera and see the invisible? Another use of night vision cameras that you might not be familiar with is their ability to see through smoke and dust. Fire departments commonly use cameras like these to find people trapped in smoky rooms, or to pinpoint the exact location of forest fires through clouds of smoke. So how do these things actually work? What are we really seeing when we look inside a night vision camera? Well, it may surprise you to learn that everything in the universe emits some kind of light. It's just not the kind of light we're used to thinking about. The sun, for example, our star, emits visible light. That's why our eyes evolved to detect that kind of light. But that's not the whole story. I'm sure you're familiar with all the different kinds of visible light, all the colors from violet to red. But there are actually lots of other kinds of light that our eyes aren't sensitive to. The reason all the colors of light are different is that they have different energies. And what you see here is that the light has different wavelengths. The blue light, for example, has a higher energy, so it has a shorter wavelength. The red light, on the other hand, has less energy, so it has a longer wavelength. But that's just the light we can see with our eyes. That's not all there is. The shortest wavelength light are gamma rays, which can have wavelengths smaller than an atom. The longest wavelengths are radio waves, which can have wavelengths larger than the entire Earth. The kind of light an object emits depends on its temperature. We're used to thinking of something hot giving off light. But it might surprise you to learn that objects that are cooler, like myself, give off a kind of light too, and that's what a night vision camera can pick up. That sort of light is called infrared light. The world sure looks a lot different in infrared light. Remember that what you're actually seeing is temperature, so something that's warm is going to look bright in the infrared. And something that's cold looks dark. Ice cream. Blow dryer. And infrared radiation is actually a measurement of temperature. Places on my face that are cold, like my nose, appear dark in an infrared camera because they're giving off less infrared radiation. And places that are warm, like my mouth, or the hair next to my head, are brighter because they're warmer. You can even see my breath in my nose if you look carefully. And this is an ice cube. Infrared light also has a lot of really interesting properties that visible light doesn't have. For example, it can often pass through things that block visible light entirely. I have a black plastic bag, and as you'll notice, you can't see through it at all. But with an infrared camera, there's no problem.
All right, so hopefully it was a little summary of all the different types of light. And again, we focus on infrared light, which is just longer wavelength, a little longer than visible light, that the light that we cannot see. I mean, it is light that we cannot see. And as she said, it picks up heat. That's just in the sense that things that are warmer will be emitting more light. So they will look brighter even in the infrared. Things that are cooler emit less light, so they will look darker in infrared. So if we go back to a couple of lectures ago to when we asked the question, so if stars are born in places that are dark and hidden, if you remember, dust was a really good thing because dust could actually shield entire regions from the light of other stars. And that meant those regions stayed cooler, a lot colder actually. And also so that gas pressure was not very strong. And it also could have things like molecular hydrogen so that, the density was higher and then gravity could be the winner. So when you have gravity winning over gas pressure in a cloud of gas, that's when you get star formation. And those were all the good things about dust. But the problem with dust is that it also blocks our view of what's happening behind the dust, right? So back to the question, if stars form in places that are so dark and hidden with dust, then how do we study them? How do we know how stars are formed? How do we test our theories? And so this is where infrared light is so useful. And just like the video was talking about, infrared light is affected much less by dust particles than visible light, just like for somewhat different reasons. But the plastic bag that she shows, right, where you can see her hands in infrared light, because the molecular composition of the plastic bag is such that infrared light can go through that. But much more relevant to the study of astronomy The example that she gave with the firefighter, where with the visible camera, you saw a bunch of smoke and you can't see through it. And smoke is kind of similar to dust in the universe, right? Because it's all those particles that are flying around that do not allow you to see through it. So instead, if like firefighters, you use a thermal camera really means an infrared camera. If you look at the exact same thing with an infrared camera, you're going to be able to see through the dust. And on top of that, because this person is warm, it has a certain temperature that emits infrared light, then you're going to be able to see them even better. So again, just to remind you, the electromagnetic spectrum, the type of light that you get depends on the wavelength of light, and it starts from the highest energies, shortest wavelengths, which is gamma rays, X-rays, then ultraviolet visible, which is the one that we can see with our eyes, and then infrared. And infrared is longer wavelengths, and it allows you to see through things like dust, through like smoke in this case, and particularly dust, right? So how does that help in the study of star formation? Well, again, dust grains are the culprits, right? They're the ones that are blocking our view of things. But if you have light that has a wavelength that is long enough, like infrared light. So infrared light has a wavelength that is a little bit bigger than dust grains. So it is possible for a wave of light to actually bypass dust grains. And of course, it's not going to be able to bypass all of them, right? But it'll probably be able to bypass many of them and many of the dust grains. So that's why you are able to see better through a screen of dust or of smoke. Notice here that you still see some of the smoke, right? It doesn't become completely invisible, but you can see enough that you know that there is a person there. So same thing with when you're looking at a region of star formation, a lot of the light that is coming from behind the dust can make it all the way to your eyes or to your telescope. So here's an example of how this works. These are Hubble Space Telescope pictures. And the one on the left is taken with a visible camera, with a camera that is sensitive just to visible light, like the one that we see with our eyes. The one on the right is an infrared camera. It is the exact same picture. But notice how with the visible one, you see a lot of the dust and, and the gas and it's just a nebula. And you see a few stars, especially the brightest ones right in the center. But when you turn on your infrared camera, then you can see a whole bunch of stars that are right behind this. And if you got here early and you were looking, if you saw part of that Leonardo DiCaprio video that I was showing, they actually are going through this nebula and showing how there's a lot of stars that are just forming right in this particular nebula, which is the Orion Nebula. And so when astronomers invented these infrared cameras for astronomy, all of a sudden it opened a window where we could actually see the places where baby stars are being born. Here's another example. This is what is called a dark cloud, where you can't see any stars at all. And this is taken at shorter wavelengths. But as you take pictures at longer and longer wavelengths, right? So this is longer and longer, you start to see more and more stars. And by the time you get to the infrared, so this is an infrared wavelength, you can see right through it. This is a particularly small clump of gas and dust. So you can really see a lot through it when you use an infrared telescope. This is another picture taken by an infrared space telescope that was used a lot to study regions of star formation. And here again, look at the difference between the visible, where you cannot see a lot of this nebula. In the infrared, you can see a lot of the nebula still, but you see the stars. You see all those baby stars that are being born right here in the. This looks like a chicken to me that is running, and so in the head of the chicken, you can still see a lot of stars, and you see the dust. And why do you see the dust? Well, the dust gets warm, and because it has a temperature, because it is warm, it also emits infrared light. So it actually looks bright in the infrared. By the way, this is a question that I get often, which is about the colors that people use to show infrared pictures. And so I just want to point out the fact that the colors are assigned artificially, right? We would not be able to see an infrared picture because our eyes don't see infrared. So in order to be able to see it, you have to artificially color it, right? The pictures are taken, like I showed you before, in black and white. And then we artificially color them. And so we do the same, and we could have chosen, I mean, people could have chosen blue, they could have chosen, pink or yellow, whatever they want. And so don't be confused by that. Same thing here, right? These are infrared. You would not be able to see it with your eyes, but they artificially color it, certain color, so that, so that we can actually see it. Here's another beautiful example, the Carina Nebula, again, with the Hubble Space Telescope. On the left, you have the visible light, the one that you can see with your eyes. On the right, artificially colored, you can see what you would be able to see in the infrared. And here's a very famous nebula, the Eagle star-forming region. They've also dubbed it the Pillars of Creation. And this is what it looks like these pillars of gas and dust, where lots and lots and lots of stars are being formed. But without infrared, you wouldn't be able to see much. Whereas when you look at it in the in the infrared, then you can see right through them, and you can see all the stars that are being formed inside of these pillars. I love this one. It looks very appropriate for Halloween. It's like very ghostly, right? In the infrared, sorry, versus what it looks like in the visible light.
Yeah,
I have a
Professor,
question.
Yep.
So in opposite way, we can see nothing if we use the ultralight camera, right?
If you were to use an ultraviolet camera, you would see different things. You would see the things that are hotter. So you would not be able to see through these columns of light. But you're right in asking about other types of light. We do use them in astronomy. We use X-rays, we use gamma rays, we use radio waves, and each one of them probes a different thing. So in very general terms, X-rays probe very high energy light, and radio waves probe very low energy light, and everything in between.
Okay, thank you.
Jacob?
I was just going to say that I was going to comment, yeah, the second image for the Pillars of Creation looks deeply haunting.
Yes, it really does. Save it.
It's much, much more ephemeral. I love it.
Take a screenshot for Halloween. So in summary, infrared telescopes have made a huge difference in being able to study regions of star formation. And a lot of what I'm going to tell you, I mean, a lot of what I already told you about how stars form and the next few slides it's only been possible to learn about that because of infrared telescopes. So I have a few here, some ground-based on Mauna Kea, like the Keck telescope and the NASA telescope. This is a future telescope, the James Webb Space Telescope and the Spitzer and all this is a telescope that already died, and this one too, but these have all been telescopes that have looked at many different things, but among them regions of star formation where we learn how stars form. So now I can tell you with a little more evidence how stars actually form. So we talked about how stars form in big clouds that are called molecular clouds, where there's a lot of dust and they are dense and cold and gravity wins. And so this is a simulation where astronomers have put in all the physics, right? They simulate the gas by using particles, and they put all the physics in them. They feel the gravity. It works like in real life, right? It's just a simulation. And so if you were to start with a spherical molecular cloud, and then you give it a little perturbation where gravity starts to win over gas pressure, this is more or less what it would be like. This process would take millions of years. So this is why they write simulations, because we can't sit down and wait until the whole process happens. But we're able to look at different places in the universe and then compare it and make sure that this picture is actually accurate. And so you can see how some parts of the cloud begin to collapse and become denser and denser until little baby stars are formed. And, oh, I didn't mean to do that. Let me go back to where we were. So you can see the little stars being formed. And as they form, because they have gravity and everything is spinning, remember? So they're spinning and they're circling around, and the gravity of some of them kicks others out of the path, and you can see how some of them spread, but the majority of them stay together and they form what is called a cluster. So this is when you see a lot of stars together, we call those clusters. And this is what a region of star formation looks like at the beginning. Like all of those beautiful pictures that I've been showing you, they all more or less have this going on in their centers at different stages, right? So you see a lot of baby stars and then still a lot of the cloud that is left around them. So this is an actual picture of one of these regions of star formation in the process. So you can see the same idea, lots of little baby stars in the center, surrounded still by a lot of the cloud. And so you could see how there were a lot of regions in that simulation that become denser and they form clumps. And then stars are eventually born out of each of those clumps that are being born everywhere. So each of these clumps that is going to form a star, as gravity compresses them, as gravity causes them to contract, they become denser and they become hotter, right? So we talked about how, if you increase the density, if you squeeze stuff together, it'll get hotter. And so they get hotter, and at some point they get so hot that their gas pressure begins to increase, right? Hot gas has higher gas pressure. So there's the two competing things. At first, gravity is the one that wins. Gravity is making the nebula or the clump become smaller and smaller until it gets so hot that it pushes back, right? So then gas pressure increases and it stops the collapse. At this moment, we would call that little clump a protostar. So a protostar is a star in the process of forming. It's after it has collapsed. So it's now a nice sphere, right? It looks like a star, but it's not quite a star. And the big difference between a star and a protostar is that a star has fusion. A star is defined as what makes a star is the fact that it has fusion in the core, right? It's fusing hydrogen into helium, or as we will learn later, it might actually be fusing something else. But a protostar, it's almost there. It's nice, it's hot, it's keeping gravity from collapsing it, but it hasn't quite started fusing. So again, as I told you before, proto is like almost, it's almost there. So it's almost a star. So the small protostar continues to accumulate or accrete more material. And as it gets more material, it keeps heating up. It keeps getting more massive, and that extra mass gives it more gravity, and it squeezes things together more, so it gets hot. Eventually, it will be hot enough to fuse hydrogen into helium, and the protostar becomes an actual star. But here's the little segue into exoplanets. And as you remember, as the protostar is forming, it inherits the rotation from the nebula, right? You saw it in the simulation. Things are sort of rotating. Everything is rotating. So each one of the clumps is rotating. And as it shrinks and it becomes a protostar, it's still rotating. So as you may remember from when we talked about the solar system formation, since it's rotating, as it shrinks, it speeds up. And because it speeds up, it flattens into a disk. I mean, the protostar in the center continues to be spherical, but the rest of the cloud becomes a disk. And we do see disks around young stars, right? Now that we have our infrared telescopes and we can look at these regions like the Orion Nebula right here. If we look at individual baby stars as they're forming, we do see disks. So these are infrared pictures, and they seem to have a disk around them. And if you compare it to the size of our solar system, they're about the same. They're about the size of a solar system, a little bigger sometimes, or a lot bigger sometimes. And so it is quite possible that planets are being formed in these disks as we speak. So we do see disks a lot in many places. So here are other examples. Here's a disk. There's a disk over there, a disk here, and a disk here. And so disks around young stars are very common. We do see them everywhere. And so for many years, the question was, well, is it possible that that maybe many stars have planets? Not the baby stars, but the more evolved stars, the older stars. Is it possible that other stars have planets? And of course, now you guys know that the answer is yes. But a little while ago, or a couple of decades ago, people didn't really know. So this is what we called exoplanets or extrasolar planets. So an exoplanet is any planet that is going around stars other than our own, right? So when we say just planet, plain planet is the planets that are going around the sun. But if we say exoplanet, then it is a planet that is going around some other star. So how do we detect them? How do we see them? And the answer is that it is very hard. It's very, very hard. And this is why we didn't know about this before. And you need to consider the scales involved in this. So let me just put it to scale, right? If the sun, right, that gigantic big sun that we talked about last week, if that were the size of a tennis ball that I can hold in one hand, at that scale, the Earth would be the size of, the tip of my pen. That's the size of the Earth compared to a tennis ball. So let me ask you, where do you think at this scale, where would you find the nearest star, right? The star that is the absolute closest to us, which is called Proxima Centauri. Where do you think it would be? So let me get the poll. How do I get another one? Okay, here we go. So where do you think the nearest star would be at this scale? So answer A, Moreno Valley. Answer B, Los Angeles. Answer C, San Francisco. D, Seattle. E, Alaska. So if the sun were the size of a tennis ball, Earth would be the ball on a ballpoint pen. And at this scale, where would you find the nearest, the absolute nearest star to the sun? And A, Moreno Valley. B, Los Angeles. C, San Francisco. D, Seattle. E, Alaska. All right, so I think you guys are just going with the absolute furthest. So most people said Alaska. And the right answer, the correct answer is actually Seattle. So not quite so far. So not Alaska, but Seattle, which is 1,100 miles away from Riverside. That's a long way. I mean, just think about it. So there's a tennis ball sitting in Riverside, and then there's nothing between, except for the interstellar medium, but there's nothing. There's no other stars at all. And then there's another tennis ball in Seattle. So crazy distances, right? And then you're trying to see something that is in Seattle from here, and that is about the size of the point, of the ball in a ballpoint pen. So it's crazy. On top of that, stars are billions of times brighter than the light that their planets reflect. So you're trying to see this tiny little planet that is much smaller than the star. It's also much dimmer. And so you put it far away, you put it in Seattle, right? And then you try to see the tiny little bit of light that is reflected, and you're just overwhelmed by the brightness of the star. So for these reasons, because it is so challenging to be able to see them, even though, you know, telescopes were invented in the 1600s, and for centuries, we weren't able to see other planets around other stars. And in fact, the very first one was discovered in 1995. And, you know, for many years, it was only like a few that were known. So how did they do it? How do we detect exoplanets? So we'll save that for after the midterm. And so come back on Wednesday and we'll talk about that. So have a great weekend, and I will be happy to stay behind and answer questions. Ian has office hours on Monday at 3 p.m. So if you have any last minute questions before the test, you should go to Ian's Zoom office hour. And again, I'll be happy to answer questions right now. So have a great weekend. See you guys.
I have a question.
Let me stop recording.
In